So the last thing we need to discuss is what happens if it's not an alternating series, and obviously we can't just look at the next term. Well, a French guy named Lagrange came up with the following formula. He said that the error for a non-alternating Taylor series has to be less than the following form. N plus 1 factorial on the bottom, x minus c to the n plus 1, and then the top here is the n plus first derivative of f evaluated at z. This is what's known as the Lagrange form of the error. The most confusing part is going to be this part. Let me give you some idea where it comes from. If you remember, the Taylor series centered about x equal to c is sigma n equals 0 to infinity, the nth derivative evaluated at c over n factorial x minus c to the n. It looks like the next term for this series, except for the derivative is evaluated at z. So how do we choose this? What we do is we choose z such that that derivative is at a maximum, such that the derivative, so the n plus first derivative at c, is at a maximum, and z has to be between x and c, so between the value you plug in and the center. The proof for this and the derivation of this, there's different ways to go at it, but one way uses the mean value theorem, and one way actually uses integration by parts and some induction, and you can take a look at that on your own if you want. So this is all a little bit confusing, so let's take a look at some examples that might clear it up. The first problem that is not alternating is problem number 5 in the handout, because if you remember, e to the x looks like this, 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So right away already we can see it's not alternating, and e to the 0.3 would just be 1 plus 0.3 plus 0.3 squared over 2 factorial plus ... And we're taking this to the fourth order. So if you remember what the formula looked like, we said that the error has to be less than the n plus first derivative evaluated at z over n plus 1 factorial x minus c to the n plus 1. So we just actually need all the different pieces to plug in. So the things I need is I need to know what my function is, I need to know what my order is, I need to know what value I'm plugging in, and I need to know my center. So the function is pretty easy. It's e to the x. The order here, it says fourth order, so n equals 4. X that we're plugging in is 0.3, and this is actually a Maclaurin polynomial, so we're centered at 0. So let's take a look at what it looks like with everything plugged in. So with everything plugged in, we're saying that the error has to be less than, we'll worry about the top part later, but down here I got 4 plus 1 factorial. X minus c looks like 0.3 minus 0 to the n plus 1, which is 4 plus 1. The top part is the most confusing part, but I luck out. I'm looking for essentially the n plus first derivative, or in this case the fifth derivative of e evaluated at z. But we luck out because the fifth derivative of e is going to be e. So it really comes down to, can I pick a value of z that is in between the center, which is 0, and the value we're plugging in, which is 0.3, which will make that the biggest? Well, it turns out the biggest will occur if you let z be 0.3. If you look at this, this is actually a pretty bad example because we're assuming that we're trying to approximate e to the 0.3, but in analyzing the error, we actually have to calculate e to the 0.3. Let's look at the next problem. It says determine how many terms are needed to approximate e squared using the Maclaurin series. So let's see what we know. We know the function is e, and we actually don't know what it is, so we're going to have to figure that out. I know that the value we're plugging in is 2, and I know this is centered about 0 because it's a Maclaurin series. So if we plug into the formula, we're looking at the n plus first derivative at z, which again, I don't know what n is, so it's still a variable, n plus 1 factorial on the bottom, and I have 2 minus 0 to the n plus 1. I would like that to be less than 0.1. So we luck out again because the nth derivative of e, no matter what it is, or the n plus first derivative of e is still e, and we got to pick a value between 0 and 2 that will make that the biggest, so I'm going to pick e squared. So here's what we have. We're saying that the error, which is e squared over n plus 1 factorial 2 to the n plus 1, has to be less than 0.1. So you have two options. You can either plug in different values of n and see which one is less than 0.1, or you can graph it on the calculator like the other problems and see when that occurs using the table function. So let's look at some problems that involve sine and cosine. It's important to know that once you shift cosine away from 0, it's not going to be alternating anymore. In fact, in the homework you saw that it went something like plus plus, minus minus, plus plus, minus minus. And so we can't use the next term, but we have to use Lagrange's form of the error. So we need four quantities. Again, we need the function, we need n, we need x, and we need the center. The function, easily enough, is cosine. N, it says third order, so n equals 3. X that we're plugging in is 5 pi over 12, and the center here is pi over 3. So plugging everything in except for the top part of the fraction, I have a 3 plus 1 factorial on the bottom. My x is 5 pi over 12. My c is pi over 3. And that's going to be raised to the 3 plus 1 power. Now, cosine is a bit tricky. In this case, we are going to need to find the fourth derivative of cosine, which is just cosine, and find its maximum between 5 pi over 12 and pi over 3. However, we can use the fact that cosine at most will be 1. So remember, this is just estimating what the error is. So we can't really always find the exact error. So the easiest thing to do for sine and cosine is just replace whatever derivative it is with 1. Makes life easier, and that's perfectly acceptable in our analysis. Let's take a look at the problem below that. Determine the number of terms needed to approximate cosine of 0.8. So here's a situation where I know my function is cosine, my n is unknown, my x that I'm plugging in is 0.8, and in this case my center is pi over 4. So same as before, my error down here, I don't know what n is, so I'm going to go n plus 1 factorial on the bottom. My x is 0.8, my c is pi over 4, and I'm raising that to the n plus first power, and I would like this to be less than 0.0001. Cosine, I don't know which derivative it is because I don't know what n is, so because cosine or sine, the greatest they can be is 1, we're just going to replace the top with 1. And again, you can do this on your calculator, use the table function, or guess and check.